Hello, welcome to today's session on dynamic programming. Today, we're going to explore a fun and interesting problem called the path with maximum gold, also known as the Goldmine problem. This problem is a great way to understand how dynamic programming can help us optimize paths in a grid. Let's get started step by step. Problem statement. Imagine we have a grid of size m by n, where each cell contains a certain amount of gold. We're a gold miner starting from the first column, which is any row in column 0, and our goal is to collect as much gold as possible. The catch is that we can only move in 3 directions. Right to the next column in the same row. Right up to the next column, 1 row up. Right down to the next column, 1 row down. We can start from any cell in the first column, which is column 0, and we must reach any cell in the last column, which is column n-1. Once we collect gold from a cell, we take it all. But in this problem, we'll assume we can only visit each cell once, with no revisiting. Our task is to find the maximum amount of gold we can collect along any valid path from the first column to the last column. For example, consider a 3 by 3 grid. If we start at row 2, column 0, which has a value of 7, we can move to row 2, column 1, which has a value of 8, then to row 2, column 2, which has a value of 9, collecting 7 plus 8 plus 9, which equals 24. But is this the maximum? We need to try all starting rows and paths to find the best one. Let's explore how to solve this systematically. Possible approaches. Let's think about how we might solve this problem. Here are a few approaches. Brute force, recursive approach. We can try every possible path recursively. Start from each cell in the first column, and for each cell, explore all 3 possible moves. Right up, right down, to the next column, continuing until we reach the last column. At the end, we take the maximum gold collected across all paths. However, this approach leads to a lot of overlapping subproblems. For example, if 2 paths converge at the same cell, we'd recompute the maximum gold from that cell onward multiple times. The time complexity is exponential, roughly O of 3 to the power m times n, since each cell branches into 3 possibilities, and we have m times n cells. That's way too slow for large grids. Greedy approach. A greedy approach might involve always choosing the cell with the maximum gold in the next column. For example, from row 1, column 0, we look at the 3 cells in column 1. Same row, row above, row below, and pick the one with the most gold. But this doesn't guarantee the maximum overall gold. A cell with less gold now might lead to a path with much more gold later. Greedy doesn't work here because we need a global optimum, not just local decisions. Dynamic programming approach. Since the brute force method has overlapping subproblems, dynamic programming can help us solve this efficiently. We can break the problem into smaller subproblems and store their solutions to avoid recomputation. Dynamic programming can be applied either top-down with memoization or bottom-up with tabulation. This will be our optimal approach, and we'll explore it in detail. Intuition for the optimal dynamic programming approach. Let's build intuition for the dynamic programming solution. The key insight is that the Goldmine problem has optimal substructure and overlapping subproblems, making it a perfect fit for dynamic programming. Imagine we're at a cell, I, J, in the grid. The maximum gold we can collect starting from this cell and moving to the last column depends on the maximum gold we can collect from the cells we can move to in the next column, which is J plus 1. Specifically, we can move to I, J plus 1 if we're going right. We can move to I minus 1, J plus 1 if we're going right up, if I minus 1 is greater than or equal to 0. We can move to I plus 1, J plus 1 if we're going right down, if I plus 1 is less than m. Let's define memoized table at I cross J as the maximum gold we can collect starting from cell I, J, and reaching any cell in the last column. If we're already in the last column, where J equals n minus 1, the maximum gold is just the gold in that cell. Memoized table at I cross J equals grid at I cross J. For any other cell, I, J, the maximum gold is the gold in the current cell plus the maximum gold we can collect from the next column. Memoized table at I cross J equals grid at I cross J plus the maximum of memoized table at I cross j plus 1, memoized table at I minus 1 cross j plus 1, memoized table at I plus 1 cross j plus 1. Considering boundary conditions for I minus 1 and I plus 1. Since we can start from any row in the first column, we need to compute memoized table at I cross 0 for all rows I and take the maximum. The catch is that we need to compute the memoized table from right to left, from the last column to the first, because each cell's value depends on the cells to its right. This suggests a bottom-up dynamic programming approach where we fill the table column by column, from the last column to the first. Visualization, example with table. Welcome to the Goldmine visualization. On screen, you see our 4x4 grid of gold amounts and an empty memoized table beside it. We'll fill this memoized table from right to left, showing how we find the maximum gold collectible. Initialization of last column. First, we handle column 3, the far right. In the memoized table, each cell in column 3 simply equals the gold in that same grid cell, since there's nowhere further to move. So memoized table at 0 cross 3 equals 5, memoized table at 1 cross 3 equals 1, memoized table at 2 cross 3 equals 3, and memoized table at 3 cross 3 equals 2. Notice how that fills the last column of the memoized table. Filling column 2, j equals 2 next, we move one column to the left, to column 2. For each row I, we look at 3 possible next cells in column 3, directly to the right, right up, and right down. We pick the largest memoized table value among those legal moves and add grid at I cross 2. For example, at row 0, we compare memoized table at 0 cross 3, which is 5, with memoized table at 1 cross 3, which is 1. Right up is invalid. The larger is 5, so memoized table at 0 cross 2 becomes grid at 0 cross 2, which is 1 plus 5, giving 6. We repeat this for rows 1 through 3, filling in memoized table at 1 cross 2 equals 9, memoized table at 2 cross 2 equals 5, and memoized table at 3 cross 2 equals 4. After that step, column 2 of the memoized table reads 6, 9, 5, 4. Filling column 1, j equals 1. Now we fill column 1. For each row I, we again examine memoized table at I cross 2, right, memoized table at I minus 1 cross 2, right up, and memoized table at I plus 1 cross 2, right down, whenever those indices exist. Take row 0 as an example. We compare memoized table at 0 cross 2 equals 6 with memoized table at 1 cross 2 equals 9. Right up is invalid. The larger is 9, so memoized table at 0 cross 1 becomes grid at 0 cross 1, which is 3 plus 9, which equals 12. We continue with row 1. Compare memoized table at 1 cross 2 equals 9. Memoized table at 0 cross 2 equals 6. Memoized table at 2 cross 2 equals 5. Choose 9. So memoized table at 1 cross 1 equals grid at 1 cross 1, which is 2 plus 9 equals 11. Similarly, row 2 becomes 9 and row 3 becomes 11. Now column 1 reads 12, 11, 9, 11 in the memoized table. Filling column 0, j equals 0. Finally, we fill the first column. Again, at each row I, we look at memoized table at I cross 1, right, memoized table at I minus 1 cross 1, right up, and memoized table at I plus 1 cross 1, right down, when valid. For row 0, we compare memoized table at 0 cross 1 equals 12 and memoized table at 1 cross 1 equals 11. The larger is 12, so memoized table at 0 cross 0 equals grid at 0 cross 0, which is 1 plus 12 equals 13. Row 1 compares 11, 12, and 9. Pick 12 plus grid at 1 cross 0, which is 2, equals 14. Row 2 chooses the larger of memoized table at 2 cross 1 equals 9. Memoized table at 1 cross 1 equals 11. Memoized table at 3 cross 1 equals 11. That's 11 plus grid at 2 cross 0, which is 5, equals 16. Row 3 picks between memoized table at 3 cross 1 equals 11 and memoized table at 2 cross 1 equals 9. 11 plus grid at 3 cross 0, which is 0, equals 11. At the end, the first column reads 13, 14, 16, 11. Final dynamic programming table. Here's the completed memoized table. Each entry memoized table at I cross J represents the maximum gold collectible if we start at cell IJ. We see column 0, 13, 14, 16, 11. Column 1, 12, 11, 9, 11. Column 2, 6, 9, 5, 4. Column 3, 5, 1, 3, 2. Finding the overall maximum. To get the best total, we look at column 0's entries, 13, 14, 16, 11. The highest is 16 at row 2. That means the optimal starting cell is row equals 2, column equals 0. Tracing the optimal path, starting from 2, 0, we collected grid at 2 cross 0 equals 5. From there, we move right down, right, or right up in column 1, whichever memoized table value was chosen. In this case, memoized table at 1 cross 1 equals 11 matched the best next step. So we go to 1, 1, and add grid at 1 cross 1 equals 2. Next, from 1, 1, we look at column 2. Memoized table at 2 cross 1 equals 9 was the best among right up, right down. So we move up to 1, 2, and add 4. Finally, from 1, 2, we move right to 0, 3, and add 5. That path, 2, 0, to 1, 1, to 1, 2, to 2, 3, collects a total of 5 plus 2 plus 4 plus 5 equals 16 gold. Our highlighted cells show the exact path through the grid that yields the maximum 16 gold. That completes the Goldmine dynamic programming visualization. Here's the pseudocode for the bottom-up dynamic programming approach to solve the path with maximum gold problem. Create a memoized table equals array of size m by n. Base case. Last column, j equals n minus 1. Fill the memoized table from right to left. Consider the 3 possible moves. Maximum gold from this cell equals current gold plus max of next cells. Find the maximum gold starting from any cell in the first column. This pseudocode builds the memoized table iteratively, starting from the last column and working backward to the first column, then finds the maximum gold by starting from any row in the first column. Let's analyze the complexity of our dynamic programming solution. Time complexity. We're using a 2-dimensional table of size m by n. We fill each cell exactly once using 2 nested loops. One for j from n-2 down to 0, which is n-1 iterations, and one for I from 0 to m-1, which is m iterations. Each cell computation takes constant time with a few comparisons and a max operation. So the total number of operations is m times n. Therefore, the time complexity is O of m times n, where m is the number of rows and n is the number of columns. This is much better than the exponential time of the brute force approach. Space complexity. We use a 2-dimensional table of size m by n to store the maximum gold for each cell, so the space complexity is O of m times n. However, we can optimize this to O of m by only storing 2 columns at a time, the current column and the next column, since each cell only depends on the cells in the next column. But in our implementation, it's O of m times n. That's it for the path with maximum gold problem. We've seen how dynamic programming helps us find the maximum gold efficiently by breaking the problem into subproblems and building a solution from right to left. Thanks for learning with me today.